This problem is about finding interfacial concentration for gas-liquid mass transfer. Consider a steady-state mass transfer process between well-mixed liquid and vapor phases of a binary mixture comprising of components A and B. The mole fractions of component A in the bulk liquid, that is XA, and bulk vapor OA are 0.36 and 0.16 respectively. The mass transfer coefficients for component A in liquid and vapor phases are 0.1 mole per meter square second and 0.05 mole per meter square second respectively. The vapor liquid equilibrium can be approximated as y star equal to 2xa for xa less than 0.4. The mole fraction of A in the liquid at the interface is, that is, we need to find the interfacial mole fraction of component A. Okay. So the formulas known to us are, this molar flux is equal to ky into y minus y star, where ky is mass transfer coefficient, overall mass transfer coefficient based on vapor phase. This is applicable for transfer occurs from gas to liquid. And the same thing we can also write in terms of overall mass transfer coefficient based on liquid mole fraction. This molar flux is overall mass transfer coefficient based on liquid mole fraction is kx, there is a kx multiplied by x minus x star. This is for useful for mass transfer occurring from liquid to gas. Of course, gas or vapor doesn't matter here. Okay, otherwise we are dealing with vapor liquid instead of gas liquid. Okay, doesn't matter much here. And we know the formula, this 1 by ky is the resistance. 1 by ky is a resistance term. 1 by resistance in terms of overall resistance. Overall resistance in terms of this gas phase vapor phase mole fraction is equal to resistance in the gas phase plus m into resistance in the liquid phase. Okay, and this is simply resistance equal to resistance in gas phase plus m into resistance in the liquid phase. Otherwise we can simply, otherwise how to understand, memorize this formula or understand this formula. This we considered as y equal to m into y equal to 1 plus mx. Otherwise, see, wherever this y is coming, there will be m into x. So here this 1 by kx is actually x in terms of resistance. No? Okay, the same thing in terms of overall mass transfer coefficient in terms of liquid phase mole fraction is, this is 1 by kx, that is equal to 1 by small kx, which is actually the the mass transfer coefficient for the liquid phase, mass transfer coefficient for the liquid phase, and this is mass transfer coefficient for the vapor phase. Here again this is x and y, how they are connected. This is actually y, this is equal to x, y equal to mx. No, that way we have to come. Say this is your y and m if you take this side, so y equal to mx. So that formula is understandable. Y equal to mx is understandable. So you consider this resistance 1 by ky. No, there is a resistance that you treated as y. This y is equal to m into x. Here this is y, that is equal to m into this is x. So if you try to remember that way, you can easily recollect this formula. Of course, 1 by capital ky is definitely equal to 1 by small ky plus the additional term, and likewise 1 by capital kx equal to 1 by small kx plus the additional term. Only this understanding this additional term, whether to have this m in the numerator or m in the denominator. So you can try to understand in the way of y. This is your y. Here this is m, and 1 by kx is the resistance of the liquid phase. That way, here this is your y, and if you take this m here, so y equal to m x. That way, somehow you can try to memorize this way. Okay, coming to the values available, we are having this small ky and small kx, which are all given as kx is 0.1 and y is 0.05, which is the mass transfer coefficient for the individual phases. Whereas this capital KOE capital KOE is mass transfer coefficient, overall, what is called as overall mass transfer coefficient based on the vapor phase mole fraction. Okay. Likewise, this is overall mass transfer coefficient. Whereas these are all individual mass transfer coefficients. That values are available. So substituting them and the value of m. What is m? M is y equal to 2x. There is a equilibrium relation. Here this m is 2. So substituting that, we get this 1 by ky, which is coming as 40, and ky is 1 by 40 available now. So likewise 1 by kx formula is written, and we get this value of kx, which is coming as 0.05, and what is available is x equal to 0.36. No, what is x? There is a mole fraction in the bulk liquid and bulk vapor. There is xa and ya. Xa is 0.36 and ya is 0.16. So xa equal to 0.36 and ya equal to 0.16. The equilibrium relation is y star equal to 2x. So we can represent this data schematically. So y versus x plot is available here. We have this equilibrium relation y star equal to 2x, and the value of y, which is 0.16, and x, which is 0.36. This is the concentration of the coexisting phases. And we can easily say that this corresponding to this 0.16 and x of 0.36, this concentration is well away from this equilibrium concentration, and transfer is supposed to happen from this liquid to vapor. Otherwise, normally in mass transfer, normally in absorption, we'll be having the inlet concentrations are somewhere here. So otherwise, over this equilibrium line, the operating line will be over this equilibrium line. Here now the operating point is below the equilibrium relation of y versus x. So otherwise, definitely we can say that the transfer is going to happen from liquid to the vapor, liquid to vapor or liquid to gas here. Okay, liquid to vapor here. So otherwise, you can say this 0.36 is definitely higher than the equilibrium concentration. Otherwise, equilibrium concentration is now corresponding to this y. What is the x? So x corresponding to this 0.16, the x is estimated to be 0.08. This is from the equilibrium relation. So otherwise, this point and this point values are now available. So using that, what is it? This is 0.36 and this is 0.08. Otherwise, we have this x and x star values, and we know the overall mass transfer coefficient based on x, which is available already, which is 0.05. So substituting that, we get this molar flux of A, which is equal to 0.014 mole per meter square second. This molar flux can also be written in terms of individual mass transfer coefficient, which is based on this liquid phase mass transfer coefficient multiplied by x minus xi. This transfer is from the higher x to the interfacial concentration value. So this interfacial concentration value is the thing to be found. Okay, so x is already known to us, which is 0.36, and kx, which is already given, which is 0.1, and xi we are going to find from equating this molar flux, which is already available. So we have now xi is coming to 0.22, what is called as 22%, or what is asked is in mole fraction only. So answer is 0.22. Thank you.